In the last part of this section, we want to talk a little bit about the difference between the washer and the disk methods, as well as do a couple more examples in order to solidify our understanding of how to use these. So far, the washer and the disk methods seem to be very similar. The washer, or the disk method rather, which was the first thing that we were looking at, in that case, we were looking at a region R which lived between some function and the x-axis. For the washer method, we were looking at a region R that lived between the graphs of two different functions. So maybe we had some f of x, and maybe we had some g of x, and we said R was the region that lived between those guys. And the formulas that we had for the disk method were something like the volume ended up being the integral. Let's separate these out a little bit. The volume in the disk method ended up being something like the integral from a to b of pi times f of x squared dx. And in the washer method, we ended up with a formula that looked something like integral from a to b of pi times f of x squared. And we wanted to make sure that we had the larger minus the smaller here, dx. So what we want to observe here is that these formulas look very similar. The primary difference is that the formula for the washer method has a g of x, whereas the formula for the disk method doesn't. And in fact, that is the only difference. If I took this green curve here, my curve for g of x, if I took that green curve to line up with the x-axis, then what I would have is exactly the same as this region over here with the same f of x. And in fact, that's exactly the difference between these two, is the disk method is a special case of the washer method where we have the function g of x being 0. So this is a special case of the washer method. And that special case has g of x equal to 0. Cool. So in general, a lot of the time we're going to be talking about only the washer method and excluding kind of this disk method here, because any problem that we could do with the disk method, we could also do it with the washer method. The same is not true in reverse, however. There are problems that we have to use kind of the washer method for. So we're just about always going to think about the washer method, but we are going to be using g of x equal to 0 when the disk method is the thing that maybe we would otherwise use. So washer method is more general, and we're just going to use that. Great. So let's see. So let's do a couple examples now. Let R be the region bounded by the curves y equals root log x over x, and y equals 1 over root x equals 1, and x equals 5. We want to find the volume of the solid formed by revolving R about the x-axis. So this one is going to be tricky to picture the region R. I'm not really sure what the graph of root log x over x looks like. Maybe I have a slightly better intuition for what y equals 1 over root x looks like, but it turns out we're not going to need to know what the graphs of these look like in order to actually figure out which one is larger. And that's really the key here. In order to do this washer method with the solid of revolution, we need to know which function is larger and which function is smaller. So in order to do that analysis, remember something about the intermediate value theorem, which says that when you have continuous functions, one of which is larger at one end and the other of which is larger at the other end. So when you have those two functions, if they switch order, so in other words, if f is maybe larger at the left end and g is larger at the right end, then those two functions have to intersect at some point in the middle. And in particular, what we want to do is if we can find all of the intersection points, we know all of the places where they could change order. We know all of the places where f could go from being larger to being smaller. So if we're thinking about some picture here, some interval between x equals 1 and x equals 5, in order to find which function is larger and which function is smaller, we first need to find where they meet up. So let's first find the intersection points between these two graphs. So I have root log x over x. I have 1 over root x. Notice that I know that both of these functions are continuous. So maybe that's something that we should write down first. I know that both functions are continuous. Namely, I know that natural log only has problems for negative or 0 x values. Since my x values here are between 1 and 5, I know that natural log isn't going to give me any problems. I also know that dividing by x isn't going to give me any problems. The only time that division gives you problems is when you're dividing by 0. Since x lives between 1 and 5, I know that, again, I'm not going to get any problems by dividing by those x values. Square roots are problems when I'm taking the square root of a negative number, but because the only way I can get a negative number out of this fraction is if the numerator is negative here, because x is between 1 and 5, so it's always positive. And the only way the numerator gives me a negative number out is if x is between 0 and 1. But it's not x is between 0 and 5 here, so log x is positive, and so we're taking a positive divided by a positive, and I can take square roots of those types of numbers. Great, so that's the justification for why this function is continuous. This function is continuous for very similar reasons. The only problems that we could run into here are if I have a division by 0. The only way I can divide by 0 is if x is 0. Not a problem, because x is between 1 and 5. And let's see. Oh, the other problem that I could have is if I take a square root of a negative, but again, not a problem because x is between 1 and 5. So both are continuous, which means that the only places they can change order are when they intersect. Great, so we want to find those intersection points. In order to do that, I can square both sides of this equation that I have. So I have log x over x equals 1 over x. Multiplying both sides by x gives me log x equals 1. And taking e to both sides gives me that x equals e. Cool. Remembering that e is about 2.7, I know that these two functions intersect at some point inside this interval here. So maybe here's e. Let's see, 2.7 is somewhere about here. And in order now to check which function is larger on which half of the interval, I can try plugging in the endpoints, for instance. So if I plug 1 into my function log x over x, so if I'm looking at a root log of 1 over 1, log of 1 is 0, 0 over 1 is 0, root 0 is 0. Great. On the other hand, root 1 over root x evaluated at 1 is 1. So on the left half of this interval here, I can say that 1 over root x is the larger function. Whatever it does, it's larger on the left half of the interval. And root log x over x is smaller. After e, however, if we, for instance, try plugging in 5, so you compare root log 5 over 5, and you compare 1 over root 5, if you plug these into your calculator, this one ends up rather, this one ends up being larger. I guess we could say is greater than 1 over root 5. And so on the right half of the interval, the function root log x over x is the larger function, and the function 1 over root x is the smaller function. So now we have a picture of our region. Again, it's not a perfect picture because we don't actually know what the graphs of these functions look like, but we do know which one is larger, which is the only important thing for us here. And so to compute the volume, we need to split this up into two different integrals, the integral from 1 to e and the integral from e to 5 there. So let's see. So the integral from 1 to e for the volume of my solid here, I want to take pi times the larger function squared minus the smaller function squared. The larger function is 1 over root x here, minus the smaller function, which is that root log x over x. On the remainder of the interval, from e to 5, the other function is larger, namely the function root log x over x minus 1 over root x squared. Great, so I have a large integral here. It's not pretty, but it's going to be doable at the very least. So let's see, so let's actually do this integral here. So let's see, so I've got the integral from 1 to e of, I can factor the pi out of the integral. 1 over root x squared is 1 over x, minus, let's see, I'm going to have a log x over x in this other fraction here. Let's see, plus the integral from e to 5. Again, I can factor that pi out. In this case, we have log x over x minus 1 over x. All right, let's simplify some things. So we have pi on the first integral here from 1 to e. I can combine those fractions, 1 minus log x over x dx. And I can combine the fractions in the second integral as well. Likewise, I can factor out a pi from both terms, so let's do that. Let's see, so pi times this integral plus this other integral from e to 5. This time I have log x minus 1. All right, so now we've reduced this to a problem of actually computing some integrals. For both of these integrals, I'm going to need to do a u substitution. Certainly I don't know, I can't integrate these by inspection or using a power rule or anything like that. So for maybe I'll use different letters for my substitutions here. Maybe I'll let u in the first one, I want that to be 1 minus natural log of x, because I see that the derivative of u, which is negative 1 over x, is sitting in the denominator here. So du dx is going to be minus 1 over x, which is to say that minus du equals dx over x. In the second integral, I'm going to want to do a different substitution. I'm going to want to use w equals natural log of x minus 1. Then dw dx is going to be 1 over x, and so dw is going to be, let's see, dx over x. Great, so in this, so I have pi sticking around. I have the integral from x equals 1 to x equals e of 1 minus log x, I said was u, and the dx over x is a du, minus a du. Plus the integral from x equals e to x equals 5 of log x minus 1 is w. The dx over x is this time dw. Cool. Now, finally, these are both integrals that I can do. So I have pi times a negative u squared over 2, evaluated from x equals 1 to x equals e, plus w squared over 2, evaluated from x equals e to x equals 5. And I think we're going to need a little bit more room to do some work here. Come on, here we go. Great. All right, so all of this we're going to bring on to the next page here. Let's see. All right, so u we can now replace by 1 minus log x. So this is minus 1 minus log x squared over 2, evaluated from 1 to e, plus w we can replace by log x minus 1 squared over 2 from e to 5. And now we can actually do the evaluation. So let's say we've got pi here. We're going to have a, let's see, log of e we know to be 1. So this numerator here is going to be 1 minus 1, which is 0. So at e, this evaluates to 0. Subtract the thing evaluated at 1. Well, the negatives will cancel, and I'll be left with 1 minus log of 1. Log of 1 is 0, so the numerator is just 1 squared, which is 1, over 2. So we get 1/2 for the first part of our integral. For the second part, we want to evaluate at x equals 5. I don't know what the natural log of 5 is. You can plug it into your calculator if you want a decimal. So that's natural log of 5 minus 1 squared over 2. If I evaluate at e, again I get natural log of e being 1, 1 minus 1 being 0, and so the second term is 0. Whew. All right, so after a lot of work, we end up with the volume of this solid that we formed. And this is kind of neat because, like I said, we didn't really know anything about what these graphs looked like. Yet somehow we were able to do enough work to figure out what the volume of this solid is. All right, we have one more example here. We want to look at now revolving a curve about the y-axis. So this is going to be similar, but now similar to the disk method, but now we're going to have these horizontal washers instead of these vertical washers. So this is a region that's a little bit nicer to look at than the previous one. We know what all of these curves look like. We have, let's see, if I'm drawing my axes here, we're going to have the lines y equals minus 1, which lives down here. We're going to have the line y equals 3, which lives up here. We're going to have the line x equals 2, somewhere here. And y equals 3x minus 2. So 3x minus 2 we know is a line with slope 3, y-intercept minus 2. In particular, maybe I'm interested in knowing where it intersects this blue line here. And if I plug 2 into 3x minus 2, I get 3 times 2 is 6, minus 2 is 4. So the line 3x minus 2 here is going to be pretty steep. It's going to do something like this. Let's see, that's y equals 3x minus 2. Cool. All right, so you can see here that having this geometric intuition, or this the ability to kind of draw some of these pictures, is going to be pretty important. So make sure that you're comfortable with graphing. If not, maybe spend some time working on that. So here's my region R, this purple shaded region here, and I want to revolve R about the y-axis this time. So this means that my washers are going to be, I should make this a different color here. Let's make it green. So that's y equals 3x minus 2. So the washers that I'm looking at here are going to be disks whose outer radius is blue, formed by that line x equals 2, and whose inner radius is green, formed by that line y equals 3x minus 2. and the shaded region that I have here is this. So I can say that the radius of each circle is determined by the x values here, since I'm revolving about this x-axis, or the y-axis, excuse me. So the radius of the blue disk is going to be the x value of the blue line, and the radius of the green disk is going to be the x value of the green line. But we don't have a formula telling us the x value of the green line, so we're probably going to want that. So let's take a moment to solve for it. So I'll have y plus 2 equals 3x, which is to say that y plus 2 over 3 equals x. Great. So now the area of a given disk that I'm looking at here is going to be pi times the outer radius squared. Well, the outer radius is always 2, so that's its square is 4. And I want to subtract the inner radius squared. And the inner radius, we've said, has x value, y plus 2 over 3. And so we have here the cross-sectional area of one of these horizontal washers. So now in order to compute the volume, we need to integrate this from the smallest y value to the largest y value of this region. The smallest y value is -1, the largest y value is 3. And I'm integrating the function pi times 4 minus y plus 2 over 3 squared dy. Great. All right. So strategies for integrating this, you have a lot of options here. I'm thinking maybe the easiest one is to set u equal to y plus 2 over 3. So that du equals 1/3 dy, or in other words, 3 du equals dy. And now I want to convert this integral, so minus the y value -1 is going to correspond to the u value 1/3. The y value of 3 is going to correspond to the u value of 5/3. And let's see, so now we're going to have a pi, which maybe we want to just factor out of the integral. We're going to have a 4 minus u squared, and dy is 3 du, so we can again factor kind of that 3 out and have a du here. Great, so integrating this is going to give me 3 pi times 4u minus u cubed over 3, evaluated from 1/3 to 5/3. And in the end, we're going to get 3 pi times this thing evaluated at 5/3 is going to be 20/3 minus, well, whatever 5/3 cubed is over 3. And now we want to subtract evaluated at 1/3, so 4/3 minus whatever 1/3 cubed is. I guess that's 1/27 over 3. Great. Again, if we want a decimal, we can plug this into our calculators, but we have maybe no reason to spend the time doing that here. What matters is that, again, we were able to compute the volume of this solid.